So chapter 5. Again, let me emphasize, starting from this chapter, we're going to the second part of the semester, which is basically advanced topics. And in this chapter, we focus on the quantity called energy. Okay, we start from a quantity called work. Okay, which is precisely, it should be called mechanical work. It's defined as the magnitude of the force times the distance that travel in the motion and times the cosine of theta, where theta is the angle between the force and the distance. Okay. So with that, we could have all kind of contribution of a force to the motion. If the work is positive, we have positive contribution. It could be zero, so I have zero contribution, or it could be negative. Okay, and we did some example on that. And then the next stuff we talk about is kinetic energy, which is defined as 1/2 mv squared. It's a very simple energy to understand. It basically tells you that as far as we're moving, there's a speed, we have kinetic energy, and then it's proportional to the mass as well. So the reason we use 1/2 and 2 here is we do that, we can actually relate the work done by on the object to the kinetic energy change. So this is called work kinetic energy theorem. And kinetic energy and work are both scalars. I gave an example here. Now I want to emphasize that this offered us not only some quantities, but a totally different point of view to a problem in mechanics. Previously, when we talk about mechanics, our idea was like, we start from forces, and then we do force analysis. We find the total force, and then we find the acceleration. And from the acceleration, we try to figure out the velocity and then displacement. Well, work and energy provide you a different approach. So in this case, for example, from this example, right, what you can see here, what do you need? You do not need to worry about force or acceleration. What you can see is, say here is, go to work and kinetic energy and use that concept to solve the problem. So in some sense, well, I guess when you do work, you still need to know the force, right? So because work is related to force. So if you can figure out the force, right? Force and then work, right? So when you have positive work, it's like you're injecting energy to the system. So because the total kinetic energy will increase. When you do negative work, you're taking energy away from the system. So that's like the actual contribution of the forces to the motion. Okay, they either do positive work, which means injecting kinetic energy into the system, or they do negative work, which means taking energy away from system. Or sometimes they could do just zero contribution, which means they're not relevant to the energy. Okay. Now, the next topic is called potential energy. Specifically, we talk about gravitational potential energy, okay, which is defined as mgh. I kind of explained where this come from, right? The higher the object is, the bigger potential energy it has, because potentially, when the height changes, you have more consequence. Okay? For example, if something falls from really high height, it's gonna basically crash really, really bad. Okay, so that's the consequence of having a bigger potential energy. Okay, now to understand this concept rigorously, we need to we talk about the work done by gravity in this case. As we show here, in both two cases, the work done by gravity are the same, even though the path they go through are totally different. Actually, you can show that whatever path you take, as far as the initial height and final height are fixed, the work done by gravity are the same. Okay, so and basically this is what we call a conservative force. Okay, a conservative force is the force that the work done by the force is independent of the path and only depend on the initial and final states. Okay, now not every force. Okay, let's go start from here and go from here. Okay, so I need to go to drawing here. So, well, it turns out not every force is a conservative force, but certainly in our case, gravity is a conservative force, okay? But there's other forces that are not conservative, okay? Let me ask you like an interesting question. What do you think we would call those forces that are not conservative? I mean, normally when I ask it in the classroom, some people say, liberal force? Uh, actually not. There's other kind of force we simply call non-conservative force, okay? Notice this word conservative came into like becomes convention in physics at least 100, about 200 years, you know. So maybe at that time there was no separation of liberal and conservative as we have now in America, you know, in American politics. So I mean, nobody thought about liberal or something. Maybe, I think maybe they would change it to liberals one day. I don't know, I'm kidding. So they're called non-conservative force, okay? Well, the definition is simple. As far as the work is not independent of the past, if the work done by that force depend on the past, then it's non-conservative force, okay? Now, a very good example of non-conservative force is a friction, okay? For example, if you consider like something moving on the top of table, like say if the object moving like this, there's definitely going to be friction, right? Like going to the opposite direction, and in that case, normal force equals weight. So the friction in this case, the force is kind of fixed, right? It's going to be just mu k times n, which is just mu k times mg. And then it's always going to be opposite to the path to the direction motion. So if you look from the top of the table, you have, for example, if you start from one position to another position, well, certainly depend on which direction you which path you take. Okay, the friction is going to do a different work because in both cases the forces are the same, but the distance traveled are totally different. So certainly the second path here you have more work than the first path. So friction is not a conservative force. Okay, so you're going to have a I mean, it depends on the path, and so what's the big deal of conservative versus non-conservative? Okay, actually, if the first is conservative, okay, we can define a potential energy associated with it. Okay, why is that? Okay, think about it like this. Okay, so you have a process, like let's say something moves from a certain height to another height. Okay, so from h1 to h2, right? Now, if it is a conservative force, that means the work done by gravity, in our case, gravity, right? Work done by gravity is independent of the path. So it doesn't matter how the object goes. As far as start from H1 and end up with H2, the work are the same, right? So that kind of suggests that these two states, you can define this work as the difference of the two states. Wow, Hannah, you're actually in a moving car. Oh, you're not driving, right? Okay, you're not driving. That's good. Okay. As far as you're not driving, it's good. I was like, for a second, it's like crazy. Okay. Well, I guess the signal is pretty good. The signal of your cell phone data or something. So, okay, great. Yeah. Okay. So as far, if the work is independent of the past, it suggests that we can define a state quantity that describe at every given height. So in this case, for example, we define potential energy as mgh, right? And then what you can say here is, okay, the work done in this case, following what we did before, it's going to be just mg times whatever the height difference we have. So it's going to be h1 minus h2, okay? But because this is independent of the past, it suggests that we can define the potential energy associated with each height. Then use the same definition, you see that this work equals to actually negative of change of potential energy, which is, you can say this initial potential energy minus final potential energy, okay? Because that's exactly, see, based on definition, that's exactly that, okay? So maybe let me write this explicitly here. See the expression like this, right? It's naturally to associate like this, you know? So then we can call each part of this as a potential energy associated with that specific height. like this height and this height, okay? So because the work is independent of the path, because it's a conservative force, we can define a potential energy like this. And does that make sense to you guys? I mean, you can, so what I'm trying to say here is, since the work is independent path, now in the future, instead of going through the specific procedure of calculating the work in a specific path, what we could do is just use this relation here to calculate it using the initial potential energy minus final. Okay, notice the minus sign here, right? Without the minus sign, the change normally is defined as the final minus initial. But because the minus sign here, we have initial minus final. Okay, so this is initial minus final. So so that's like give us a better way to calculate work. So we don't have to worry about a specific direction of the force and specific direction of the displacement, the detail of the path. So basically, the advantage of defining a potential energy is to simplify the calculation of work done by conservative force. However, it is impossible to do the same thing for a non-conservative force like this. Well, the reason is pretty clear. Well, because the work is actually dependent on the path, right? So you cannot define a potential energy here and here and then simply find the difference, because it would only correspond to one path work, because there's so many different paths you can take, and along each path the work are different. So work is different. So it's impossible to do that. So basically, only for conservative force we can define a potential energy. Okay. So potential energy is directly related to work done by conservative force. Is related to work done by conservative force. Okay, now you may say, we didn't solve the whole problem, right? For the non-conservative forces, we still need to go to the specific path and to calculate specific work. That is true. Okay. However, it turns out amazingly, all the fundamental interactions we have in nature, remember the four of them: gravity, electromagnetic, weak, and strong. They are all conservative forces. So nature kind of prefer conservative. So so for all these four forces, they are we can define potential energy, and we can use that to calculate the work instead of going directly to a specific path. So save us a lot of labor. Okay. Any questions so far? Okay. So as I said, for this class, okay, even in mechanics, it's possible to talk about some other kind of potential energies, like spring potential energy. Okay. However, because we are kind of limited in our time, we're gonna focus on just gravitational potential energy. Okay. So so for this class, whenever you think about potential energy, just think about gravitational potential energy. Okay. So and as we said, we define this as mgh. Okay. Let me see. Okay. So we can talk about the unit of this potential energy as well. Kilogram, right, times meter per second square times another meter. As you can tell, it's just kilogram times meter square per second square, or just Newton times meter. Same unit as kinetic energy or work. Okay, it's just in joules. Okay, as it should be. And also, it is a scalar because there's no direction for potential energy. It's just a number. Okay. Now the idea is the good idea here is that as far as we know potential energy, we do not need to worry about how to calculate work specifically, and we can just totally focus on the energy. Okay. Well, the energy concept is even easier than the work concept because you don't have to know the direction, displacement, and everything. Okay. I got a comment here. Oh. Okay. Oh, there should just somebody's explaining the situation here. That's fine. Okay. So what else? Okay. Well, there's another question we like to we need to consider here. So it is the so-called reference plane. So what is that concept? Okay, look at this definition here, right? The potential depends on the mass, gravity, and also the height. So here comes the question: at which height we use as our reference plane, which is we define as our zero height, right? Well, for example, you let's say I have a ball and I put on top of a table here, and then the table itself is sitting. I mean, is in a standing on a room, right? There's a floor here. So in this case, right, you might want to calculate the potential energy of the ball. Should I refer to the top of the table? Should I define this as my h equals 0, or should I define this as my h equals 0, right? Certainly, it's going to give you different numbers for your potential energy, right? What do you guys think? Should I do 1 or 2? Just send me a message. Okay, I got a couple answers. 2, 1, 2, 2, 1, 2. Well, okay, it's kind of divided, split it. So, okay, the actual answer in this case is it doesn't matter. It sounds crazy, right? Because obviously, when you take the different height, you got different number in potential energy, okay? But actually, it's fine. The real thing is the work done by gravity. If you consider a height change, say going from here to here, the work done by gravity will be fixed. Okay, it doesn't matter. It's independent of what height you choose as your reference plane. It's always going to be the same number. I'm going to show this in a second. So, but however, the absolute values of potential energies themselves could change depending on the height. Okay. Now you may feel like this is crazy. I could have different energies or what. It's actually not that crazy because again, my point. It's very similar to one-dimensional motion. Say you have one-dimensional motion. I mean, like one object is here, like, and then it later on goes to here. Now, if you define a origin like to be this origin right here, this may go from like say 2 meter to 5 meter. Well, if you define another origin like here, this may go from 4 meter to 7 meter. Okay. Well, the absolute values of the positions are going to be different depending on the origin, but the displacement in both cases has to be the same. It's going to be final minus initial is going to be 3 meter. That is independent of the origin you choose. Okay, that displacement is the same, although the coordinates, the positions values are different. Same thing here. When you change the reference height, the potential energy, I mean, are different, but the work done by gravity are the same. Okay, so we can easily show that. Okay, so maybe let's use that example as an example of doing calculation of the potential energy. So I think there's a better example in the book. Let me use that one in the book. Okay, so okay, this is the potential energy. Okay, there's I remember there's one example here. Maybe not this one. Okay, is that this one? I don't think so. Maybe okay. Maybe let's okay. Maybe let me use this as one example, and then I'll do another example there. Okay. So for example, let's say the height here is let me do this both cases. Okay. So first of all, let's choose the table as our reference height. Okay. And then let's say let's define a so this height here would be just let's say this is I'll just call it 1 meter. Okay. And then let's say the mass is 1 kilogram. Okay. Okay. In this case, if you calculate the potential energy, so this goes from here to here, right? It goes down like this. So the initial potential energy would be just mgh which is just 1 kilogram times 9.8 times 1 meter. Okay, so you have 9.8 kilogram meter square per second squared. That's 9.8 joule. Okay, well, what about the final? The final, when it hits the ground, right? This is 0 height, so it's simply 0. So you have these two numbers. And the work done by gravity using our definition here, using our relation is initial potential energy minus final potential energy, right? Remember, this is something we write here, like this one here, right? So, and that's simply equal to 9.8 joule minus 0, so it's 9.8 joule, okay? So that is the work done by gravity here, okay? Now let's consider the second case, okay? Let's say the table itself is 0.5 meter, okay, for simplicity. So, and then your initial height would be, if you use this as your 0 height, the initial height would be 1.5 meter, okay? And final would be 0. Sorry, final is not 0 because you hit the table, so its final is gonna be 0.5 meter. So that means your initial potential energy will be, again, mgh. So be 1 kilogram times 9.8 meter per second square times 1.5 meter. So as you see, it's going to be a little bit harder, to calculate than this one, but it's going to be 9.8 plus another 4.9. So that's going to be 14.7 joule. Okay, now the final potential energy, we can do the same. Okay, let me maybe put it like I here. MGHF, okay. So as you see here, it's gonna be 1 kilogram times 9.8 meter per second square times 0.5 meter. So that's gonna give you half of this. So it's gonna be 4.9 joule. And the difference, look at these two numbers here, 14.7 and 4.9, they're totally different from these two numbers, 9.8 and 0. But when you calculate the difference, like you get 14.7 minus 4.9, and that's gonna be giving you like 9.8. So the difference of the potential energy which give you the work done by gravity are the same, okay, like this one. So you got the same work done by gravity, okay, but the potential energy values themselves are different, okay. That makes sense, you guys? Okay. Now you understand that you can choose whatever height you want, okay? However, just for this problem, which one, after seeing this calculation, which one do you think is better choice for the problem as the reference plane? Which reference plane is better? Again, they're both good, but which one's better? Send me a message. Okay, there's still like split answers. I would say that this is maybe a little bit subjective, but I think the first, okay. Why? Because in the first case, the final potential is simply 0, and then so it's way easier to do calculation with. So see, when you only need to calculate one potential energy, the other one is simply 0. Well, in the second case, you have both non-zeros, and so the answer, the difference certainly is the same, but you have to do two calculations instead of one. So I would choose the first reference plane, because it simplify my calculation, So again, it's similar to when you solve Newton's law problem, right? Sometimes you choose remember when the object is in a ramp, we sometimes choose this as our reference, as our coordinate system. Now the reason for that is it is simpler because we only need to kind of find the component of single force, which is gravity. Most of other forces are along the two directions. Again, you can definitely choose it to be still the same like this. Okay, sorry. You can still choose it to be where is okay. like this, but it's sometimes it's just more complicated to do the problem. So I would say choose it based on your own convenience. Okay, choose the simplest one so that you don't need to do a whole lot of calculation. Okay, of this. So that's the key for choosing a coordinate system or choosing a reference plane for your potential energy. Okay. Okay, so let me see whether we do this one or not, because this one might be pretty much the same as we did. Okay, yeah. Yeah, I think this one's pretty much the same as we just did. In this problem, it's basically asking you to calculate potential energy. This guy is going from A to B, and then you have two choices of reference plane. First of all, you choose B as your reference plane. Second of all, you choose A as your reference plane. Well, in these cases, you see that the potential energy themselves might be different, but the difference of these between these two are always the same, you know, like this and this. So it's independent of the reference plane. So it's basically the same as we did. So I don't think we need to do this one. Okay. So again, for this simple problem, it also serves as an example showing you how to calculate potential energy. It's pretty simple. Just plug in mass, gravity, and then the height, and that's it. You know. Do I have any questions? Good. Okay. Okay. Let's move on. Okay. So the next topic we want to do here is now we want to combine everything together. So we're done. Topic number 4. Okay, this is gonna be called energy conservation. So let's kind of summarize what we learned from these two kind of energies. In the first case, when we have kinetic energy, we have the so-called work and kinetic energy theorem. So it says total work, let me put it like a sum, maybe like this. Total work equals to change in kinetic energy, okay? Or you really, it's basically like KEF minus KEI. And then from the potential energy here, we learned that work done by conservative force, I'll write conservative here, okay, equals to negative change of potential energy. So that'd be like PEI minus PEF. Okay, so how do we combine them? Okay, we can actually simply add these two together. Okay, if we add these two equations together, we will have no, I'm sorry, subtract. So let's subtract 2 from 1. Okay. So we have total work here, subtract the work done by conservative force. So that's going to give us work done by non-conservative force, okay? And that equals to this delta E subtract negative delta PE, delta K subtract negative delta P. So that's like delta KE plus delta PE, okay? So we reached this very interesting relation. And we define on this side, okay, we define energy, total energy equals to kinetic energy plus potential energy. This is our total mechanical energy, okay? Total mechanical energy. And then we can write this as work done by non-conservative force equals to a change of total mechanical energy, okay? So this is actually one of the very interesting results based on combining these two pieces of physics we just learned, okay? Well, and for us, mostly, well, this one can be used in general, but for us, mostly we consider a simple case, okay? When there's no work done by, when work done by non-conservative force is 0, well, when this work is 0, based on this, right, we have delta E equals 0, okay? Or we can say energy total initial energy equal to total final energy. And this is what we call energy conservation. And we probably gonna mostly you do a focus on this case. because this case here is a little bit more complicated, although it's not too much. But we'll mostly focus on this case, and because also the time limit of this course. So we'll consider this simple case, okay, which is the case we have energy conservation, okay. Now you may say, well, this is nice, but it only works when there's work done by non-conservative force 0, right? It seems like a little bit limited, but actually it applies more cases than you think of. Because think about it, right? As I explained, all the 4 fundamental interactions in nature we have are conservative forces. So that means fundamentally we have energy conservation. We include all kinds of energies we have, whatever kind of energy we have. The total energy in the whole universe is conserved, okay? Which is a really nice thing to have, okay? Because it's kind of simple. Well, you heard about all kinds of energy stuff, right? Like as I mentioned before. But essentially, basically, if you want to get some energy somewhere, you need to use some other kind of energy to convert it to that energy. You can never create energy from nowhere, okay? It's like a very, very fundamental physics law, like as we know it, okay? So it's just simply impossible, okay? You may heard about like a long time ago, people were trying to build some engines, after Industrial Revolution. Some people try to build something called perpetual motion engine. I think I got it right, but I'm not sure. Motion engine. So that basically means that this thing is gonna run by itself forever, and without using any energy input. Okay, that would be really nice, right? We can build up some engine like that. We'll just run it. I mean, does not cost any electricity, any gas, any oil, any solar energy, whatever. It just run by itself. Okay, that'd be so cool, right? And then we'll just sit there and relax. Nobody need to work in the whole world. We just build up some bunch of these engines, let it do everything for us. Unfortunately, it's kind of like too much. I mean, it's impossible. Okay, I guess so. So in some sense, energy conservation can be translated as the sentence like no perpetual motion engine can be built. Okay. And actually, it is not like something like a rule or law set up by somebody, saying you just cannot build it. Actually, it's the opposite. A lot of people tried to build this perpetual motion engine, but they all failed. It's just, I mean, they have some really clever design, but in their design, there's always a little bit of hole that they didn't realize on paper. But when they try to put it in work, it just simply failed. Okay, so if you could build a perpetual motion engine, you could be easily a billionaire because you can sell those engines to other people, right? But if you hear somebody else saying they can build one, just don't believe them. Okay, it's simply fraud. Okay, it's impossible. Okay, and well, you guys probably already know this. Okay, in our every life, there's another way to say this. Okay. It's called no free lunch, right? It's kind of saying the same thing, If you want to get somewhere, you better work hard, work your butt off. You better put a lot of work into the thing. If you want to get a degree, right, you have to take all the courses. You have to really work really hard. You just want to sit there and enjoy and relax. You're not gonna get anywhere. So there's no free lunch. Okay, I guess once in a while you do have a free lunch from somewhere. Some people were saying, okay, come here, we have free hot dogs, but these are, I mean, there's always some hidden cost. I mean, nothing is totally free. I think this is a really good way to think about it. No free lunch, like energy conservation. Okay, well, next time when you guys talk about it with your friend, instead of saying no free lunch, you could say energy conservation. That'll be like scare them totally away, because they don't know what you're talking about, but they understand this is something really deep. So they're kind of the same thing. Okay. So coming back to our class, let me give you some examples of applying energy conservation. Okay. To simplify like calculation or something. Okay. So let's start from our old friend of free fall motion. So again, let's revisit this problem, okay? So you start from initial height h naught, and then the ball simply goes down, and then at certain height h, you want to figure out the velocity of the ball, okay? Now the initial velocity here is just simply 0, okay? Now let's try to use energy conservation to solve this problem, okay? Now in order to use energy conservation, you have to do one thing. You have to check whether this is true, whether the work done by non-conservative force is 0, okay? Now in this case, as we know, the only force we have is gravity, and gravity is totally conservative force. So this condition is satisfied. So energy should be conserved, okay? How do we use it? Okay, so we write it like this, EI equals EF. Okay, as we know, each one of these could be kinetic energy plus potential energy, okay? So we write it like more specific. And then we'll use the definition, we'll put the definition here. Okay, in the problem, we know VI equals 0. So this term is definitely gone, right? This is 0. Well, HI is not 0. It's given at H naught. And VF is not 0. It's something we will find out. And HF is something given as H. Now, so we have these 3 terms here, non-zero terms. Now notice there's a common factor M for both all the terms. So if you divide M, M is gone, okay? Now we're interested in V, right? We can move this term to the left. So we plug in those H here. We have G H naught, which is the initial height, minus G HF, which we call it H here. So this is our 2 terms. Now equal to 1/2 VF squared. So let's multiply 2 on both sides of this. So the VF we were looking for is simply equals to square root of 2. I mean, we can factor out G. So we have H naught minus H. And that's it. Do you guys like this method? You better say yes, you know. Okay, again, look at what we did before, okay? Like when we use work kinetic energy theorem to solve this problem. It was here, remember? See, remember we can use this formula, we remember it right, like kinematic formula here to solve the problem, or use work kinetic energy theorem, calculate the work and set it equal to change in kinetic energy, we can solve the problem, okay? Well, on paper, it looks like not much difference, you know, a couple lines here, a couple lines there, and then in our final method, it's still a couple lines. But in terms of the concepts and thinking, this method is actually way simpler. Why? Well, I write 3 lines here, okay? Because we're doing step by step. We're doing. I mean, it's new for us. But after a while, you can, if you want, you can start from this line directly, because in any case, it's going to be initial kinetic energy plus initial potential equal to final kinetic plus final potential, and some terms might be 0, right? And these definitions are so easy to memorize. You know, 1/2 mv squared mgh. They're just so easy. After a couple problems, you just remember them. And there's no very complicated formula to memorize or anything. Okay? So, and the concept is very simple, you know, like total energy here equal to total energy there. So you can set up equations, solve the unknown, okay? So I think that this method is really, I'm not kidding, this is really the best method so far for us to solve problem, okay? So now before I do the second example, let me kind of explain using energy conservation, the motion for free fall, okay? So think about something like we threw a ball upward, right? What is happening here? So the ball goes up and then it goes maximum height and comes back, right? Let's try to understand this process using from the energy point of view, okay? So as I said, because in the whole process, there's only gravity doing work, so the total energy must be conserved, okay? So at the very beginning, when you toss the ball up, right, you can set this as your initial height so that h equals 0, so there's no potential energy here, okay? The only energy is the kinetic energy, is the initial speed of the ball, which essentially comes from the work you did to the ball, okay? Now the ball goes up, okay? But then why does the speed decrease? Okay, it's pretty simple because when it goes higher, it start to pick up some potential energy, MGH, right? So the higher it goes, the bigger the potential energy it has. But because the total energy has to be conserved, that means the kinetic energy has to decrease. Okay, that means the speed has to decrease. That makes sense? Okay, so it's gonna go all the way until, so the potential energy keep increasing, kinetic energy keep decreasing until it reaches the maximum height. When the kinetic energy becomes zero, the speed becomes zero, okay? So everything becomes potential energy here at this point. And then after that, okay, it started to go downward. When it started to go downward, the potential energy start to decrease. Well, the kinetic energy should then increase, right? Because total energy is conserved. So the velocity is going to be bigger and bigger until it comes back to the same height here. So during this discussion, we didn't use the concept force or acceleration, right? We just consider the whole thing with energy, two kind of energies and energy conservation. We can, as you see here, it provide us a totally different point of view for the problem. And a lot of times this is a simpler point of view for the problem, okay? Another thing we can understand now is why at any given height, the two velocities you have going up and going down, they are opposite in direction, but they're same in magnitude, okay? And because the energy consideration is pretty clear, because total energy is conserved. So at any given height, the potential energies at these 2 points are equal because they're the same height. That means kinetic energy has to be equal as well. That means the speed has to be the same, which we couldn't understand very well when we got this result in chapter 2, right? We were just taking it as some kind of like from symmetry consideration or something. But now from the energy point of view, it's pretty clear that they have to have the same speed at any given height because of energy, essentially. Okay, does that make sense to you guys? Any questions? Good, okay. Okay, let me give you another example so that you can appreciate this this thing even better, okay? So let's talk about another old friend, okay, projectile motion. Well, this may not be as good a friend as free fall motion because it's kind of complicated. And some of you may consider this as your enemy instead of friend. But so let's try to use energy conservation to do something. Okay? So this is the ground, okay? Suppose we threw this object away from the ground, okay? The object is gonna be going to the air. Suppose we know the initial velocity is v, okay, v naught, okay? Now our question is, at some height h, what is going to be the final velocity, final speed h at h? Okay. Well, you can solve this problem by doing the projectile motion stuff we learned from chapter 3, 2D motions, but it's going to be complicated. You know that, right? Because you need to find the components, consider each component. The x component, the velocity does not change. Y component velocity changes. And you have to use a constant acceleration formula. And then in the end, you have to put them back to find the magnitude, okay? Let me show you how easy it is to solve the problem with energy conservation, okay? So again, we use this simple relation, EI equal to EF. Now, why can't we use it? Because when something is in the air, if we ignore air resistance, there's only gravity doing work. So, and gravity is a conservative force. So we can definitely use energy conservation here. So let's write directly from the third expression, okay? At the initial position, it could have kinetic energy and potential energy, right? In the final position, same thing, kinetic energy and potential energy. Okay, now here's my question to you guys. Okay, we take this as our reference plane with h equal to 0. Which of these 4 terms is 0? Send me a message. There's a 1 term out of these 4 terms is actually 0. Okay. Okay, I got 1 response. Okay, yes, I got one answer. Anybody else want to try? There's 1 term is 0. Okay, yes, I got another one. Good. Okay, no, okay, this initial height is 0, right? Because this is where it start from. So the initial height is 0. HI is 0 here. Okay, so this is 0. Well, this is not 0 because we're talking about some arbitrary height here. So this is not 0. Okay, so this term is 0. Now from this, okay, again, you see the very simple equation here. And then actually the mass can be canceled out again. M. So you can divide M on all terms. So M's gone. And we're looking for V, right? Which is essentially VF. So again, we move this term to the left. So we have 1/2 VI squared minus GHF equals to 1/2 VF squared, okay? Now you may want to multiply 2 on both sides. So you have 2 VI, so you have VI squared minus 2GHF, okay? That equals VF squared, okay? Okay, let me use the value system. So that means VF equal to VI squared, which I call V naught squared. So V naught squared minus 2GH. Let's just use H here because H is given in the problem. So that's it. Okay, VF equal to V naught squared minus 2GH, and that's the answer for this for the problem. So I hope with this example you now kind of trust me, right? See, this is really simple, right? Compared to what you did for 2D problems in chapter 3, right? You agree? No more, components, no more constant excitation formulas, just simple setup. One equation, energy conservation, you got the answer. Right? Do you like it? Okay. Okay. So that's the answer for this one. Okay. Let me ask you this question then. Okay. If we can do things really fast like this, does that mean what we learned in chapter 3 is totally a waste of time? Shouldn't we go directly to energy like we're doing right now? What do you guys think? Just send me a message. I guess you don't want to say we did waste time because otherwise it's kind of not very polite to me, right, as the instructor. I spent a lot of time teaching you chapter 3, and then now you realize we're totally wasting our time there. That'd be kind of bad, right? Okay, I got some response here. Oh, okay, yeah, you guys be nice to me. Like some people saying like it was helpful to understand the concept, or some people saying we need the groundwork. Okay, yeah. So basically, it's like you should know doing addition, doing like 2 plus 3 first by hand, then doing it in calculator, right? So, well, this is all kind of nice, but it's actually more than that. Okay, so it's not only we need the groundwork to start from, but also even after we learn energy conservation, sometimes we still need our previous approach. Why? For one example here, okay, see what you got here is the magnitude of velocity, right? Of this velocity here. But which direction does it go? Well, energy conservation cannot tell you that, okay? It can only tell you a magnitude because direction simply does not enter in your expressions here. All of these are scalars, they all have numbers. You cannot talk about, you cannot know the direction. If you want to know the direction, you have to go back to the approach we used in chapter 3, okay? And another thing is, for example, if you want to know the time, okay, how much time does it take to go to height h? Again, we cannot get it here. See, in our energy conservation here, there's no time in here. Time is not related here. So if we want to know time, we still need to go back to chapter 3. So energy conservation give us a shortcut, okay? But there's a price you pay to the shortcut, as any shortcut you do, right? You miss a lot of stuff by taking the shortcut, okay? So I think in your life, you shouldn't take shortcuts, unless it's unavoidable or something you have to do. Because normally on the normal way going, you got a lot more stuff in there, and sometimes the best shortcut for your life is just doing everything step by step. Okay, sounds crazy, but based on my experience, that's the shortest way to do everything. Just do it step by step. Okay, if you want to try to take a shortcut, it's gonna end up costing you more time. Okay, that's normally the case. So same thing here. Well, if you want to get a quick answer about something, you know, use energy conservation like this. But if you want to get a full analysis to the problem, you know, some full information, you still need to go back to the Newton's law or kinematic. Oh, total waste time. No. Okay. Okay. Well, this is another example telling that your instructor wouldn't waste a lot of time yours to teach you something that we would totally abandon you later. You know, it's not, at least not in this level of class. You know. Okay. So hopefully these two examples kind of convince you that it's kind of useful to have energy conservation. Okay. Now let's do one exercise. We haven't done exercise for a while, so let's do one here. Okay. We have 20 minutes left, so hopefully we can get one exercise pretty well. Okay. So let's do this one. Okay. Okay. So suppose we have a very rough path here. Okay. And then leading to a horizontal surface. Okay. Well, we know there's a ball on the top here. Okay. Now let's ignore friction. There's no friction. Okay. No friction. Okay. And then we know the initial height here. Okay. Initial height to be, let me give a number here. So to be 2 meters. Okay. So let try to calculate the speed of the ball when it reaches the ground. Okay. Using energy conservation, by using energy conservation, just like we did in these two examples. Okay. Well, the mass is not given in there because it cancels out. But if you want, you can plug in mass equal to 1 kilogram or whatever mass you prefer. Okay, so anyway, so just do this problem. Okay. Okay, I forgot to mention, they start from the rest. Okay, from the rest. Okay, go ahead. I'm gonna give you like 15 minutes or so to try it. Okay. Okay, I guess let's we have 10 minutes left, so let's maybe sum it up together. So now the actually challenging part of this problem is not the solving itself using it, but in some sense, I mean, you have to verify. You can't use energy conservation first, right? Now, how do we verify that? Again, remember the condition here is if there's no work done by non-conservative force. So how many force do we have on the object? Well, as it goes downward, right, there's certainly going to be gravity. And there's going to be normal force because the contact with the surface. And because there's no friction, so that's it. There's only two forces, gravity and normal force. Well, gravity, as we know, is a conservative force. What about normal force? Well, it turns out because the nature of normal force is always going to be perpendicular to the surface and going away from surface. So no matter which part of the surface you are, the normal force is always perpendicular to the direction of motion. So therefore, the work done by normal force is always zero in this case. Does that make sense? Because going along, it will not contribute to the motion at all. So the work done by normal force is actually zero, and then the gravity is only force that doing work, and it's conservative, so we can use energy conservation. Okay, so to set up energy conservation is you can start from here, like initial kinetic energy plus potential energy equals to final kinetic energy plus potential energy. Okay. Well, you need to set up a zero reference plane for your problem, which is naturally to be this one, right? The ground is going to be the zero. So if that's the case, then because so you need to specify the two states. This is going to be your initial state. This is going to be your final state, right? This is very important for you to look at the specific states. Well, in the final states, because h equals 0, so this term becomes 0, okay? Well, in the initial state, because it starts from the rest, so this term becomes 0 because the initial velocity is 0. So there's only two non-zero terms in this problem. And there's a mass everywhere, so you can cancel out mass. So in the end, it's just like GHI equals to 1/2 VF squared, okay? And you can, I mean, if you multiply 2 and square root, so VF is just equals to square root of 2GHI, okay? Now you can plug in numbers here. You have 2 times 9.8, and then HI is 2 again. So it's 4 times 9.8. So you got, take square root, you got something like 6.26 meter per second. Okay. Now, if some of you prefer to work with numbers, there's another way to do this. So what you can do is, because you know, see what is asked you about is the final velocity here. So you don't know what is going on for the final state, but you can figure out the total energy to start from, right? Well, that's given by these two terms. So you have EI equals to 1/2 MVI squared plus MGHI, okay? Well, because VI is 0, so this term is 0. So there's only one term here, which is MGHI. But you do not know M. So what do you do? Well, as I said, because M cancels out, so M doesn't matter. That means you can give it any value. If you take M equal to 1 M, you can actually put it in here. You have 1 times 9.8 times 2. So that's going to be like 19.6 joule, okay? That's your starting energy. Now, in the end, so that's going to be safe because energy conservation, that also equal to the final energy, okay? And then what do you have for the final energy? So you have this two terms. But HF is 0 here, so this is 0. So from there, you can solve for VF, right? It's going to be a 2EF over M and square root, okay? That equal to VF. Well, you can plug in those numbers you have from EF, and then still, again, use like 1 for your mass. As you can see here, this is just nothing but this, right? The same thing. So in the end, you got the same answer. It's like 6.26 meter per second, okay? Now, I personally prefer the first way of doing it, totally formal with no symbols, and then simplified only in the end, last step, plug in numbers. But if you really hate the first one, you can use the second approach, you know. The second approach actually have a little bit better physical, I mean, it makes sense in physics, right? See, it's kind of like you can figure out one energy and then that energy stay the same. And then you can go from one state to the other state, and then you go from there to get the unknown, okay? Okay, I guess that's all. Any question about this problem? I think you love energy conservation after doing a few of these kind of problems because it's really convenient, okay? I don't want to recommend a lot of work kinetic energy theorem because that one still requires you to calculate the work, which could be still kind of painful because you need to know the angle between two directions, et cetera, et cetera. But energy conservation, no direction, no angle, no vector, no force, just some scalars in the equation. That's so good, you know. I mean, you enjoy it when you do problems, homework problem in this chapter, okay? I think we're pretty much done for this chapter, okay? I might mention just a little bit like tomorrow about a little bit the rest, but I think for today we knocked the main part of this chapter. We put everything together, you know, work, kinetic energy, potential energy, and then we have energy conservation. And energy conservation is simple, but also very important. So make sure you understand this example and then couple exercise. I mean, exercise example, and then it's definitely going to be on the second task. Okay. Okay, I got one message here. Hold on. Okay, that's fine. So I guess that's it for today. So if you guys have any questions, feel free to stay. Otherwise, I will see you guys tomorrow. Okay.